Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Molecular Beam Epitaxy under the paper Physics at Nanoscience and Technology Part 1. After completing this module, the students will be able to understand what is molecular beam epitaxy, its working principle, and what are the applications of MBE, and what are the advantages and disadvantages of the system, and who invented molecular beam epitaxy, and how it is used to fabricate the quantum dots. Molecular beam epitaxy is an epitaxial growth technique used to deposit thin film of a single crystal. J.R. Arthur and A.Y. Cho developed the technique in late 1960s at Bell Laboratories. It is extensively used in manufacturing of semiconductor devices, for example transistors, and is one of the fundamental techniques used in nanotechnologies. Molecular beam epitaxy or MBE involves taking a base material called the substrate onto which the film will be deposited. The substrate can be semiconductor like silicon, germanium, or gallium arsenide. The substrate is heated up to suitable temperature such as 500 to 600 degrees Celsius in the case of gallium arsenide. The precursor material is heated to high temperature such that it is in the present gas state. The gaseous precursor is then bombarded onto the substrate to form a focused beam of atoms or molecules. The source from where the beam is incident on the substrate is called gun or the effusion cell. For firing different type of atoms or molecules onto the substrate, different gun is needed. For example, same gun cannot be used for different materials. The atoms or molecules on reaching the surface of the substrate condense and gradually grows into ultra thin layers. Thus, the crystal usually grows one atomic or molecular layer at a time. This gives precise control over the thickness of the deposited films and makes MBE an excellent technique to deposit high quality and uniform thickness thin films over a wide array of substrates, as it comprises building up the material via atomic and molecular level manipulation. It reflects the processes carried out in nanotechnology. MBE is able to grow high purity crystals owing to the instruments and processes involved in the deposition process. It is carried out in highly controlled environment. Ultra-high vacuum and extremely clean conditions are required to be maintained. This is needed to avoid possible contamination from any dust particle or a gas molecule, as they can interfere with the growth process of the crystal. The level of cleanliness required is much higher than the standard conditions in the semiconductor manufacturing, and the required vacuum levels implies that the pressure should be as low as possible and which can be measured. MBE is analogous to inkjet printer, which produces layers of colored print on the page by bombarding jets or high-speed streams of ink from hot guns. Inkjet printers uses four separate guns to fire different colored inks such as cyan, magenta, yellow, and black. These guns gradually create the colored image of the pattern to be printed on the paper. Similarly, in MBE, different molecules are fired from different beams and they condense on the surface of the substrate. However, MBE is relatively slow, can even take hours to complete than inkjet printing. Literally, epitaxial implies arranged on top of. Thus, MBE essentially means using beam of molecules to deposit layers on the top of the substrate. Now students, let us see the working principle of MBE. MBE is performed in high or ultra-high vacuum of order 10 raised to power minus 8 to 10 raised to power minus 12 torr conditions. Deposition rate in an MBE is a critical parameter which allows the epitaxial growth of the films. Typical deposition rates are of the order of 3000 nanometer per hour. Such deposition rates demand higher vacuum conditions than other deposition conditions to achieve similar impurity levels. Owing to the presence of ultra-high vacuum environment and absence of carrier gas, this technique produces film of high purity. When solid-state precursors are used, they are heated in separate quasi-Knudsen effusion cells or electron beam evaporators till the sublimation temperature is reached. In case of gallium arsenide, elements such as gallium and arsenic in extremely pure form are used. The elements in the gas phase condense on the substrate where they can react with each other. In case of gallium and arsenide, single crystal gallium arsenide can be grown. When copper or gold are evaporated, the gas phase elements impinging on the surface of the substrate may be either absorbed or reflected. The atoms present on the surface of the substrate may be dissolved. The rate of the material impinging at the surface of the substrate can be controlled by controlling the temperature of the source. The temperature of the substrate affects the rate of molecules hopping or desorption. The term beam is used to emphasize that the evaporated atoms do not interact with each other or with the gas of the vacuum chamber until they reach the wafer. Because of the long mean free path of the atoms, the growth of the crystal can be monitored in real time by using reflection high energy electrons diffraction or known as REID. The thickness of each layer can be precisely controlled up to single atomic layer. This is achieved by controlling the on and off of the shutters present in the front of the furnace by a computer. Complex features having layers of different materials can be produced by this method. This technique has been widely used to create confined structures such as quantum wells and quantum dots. Such layers are essential for several modern semiconductor devices such as semiconductor lasers and LEDs. If the substrate requires cooling, cryopumps and cryopanels are integrated with the growth chamber in order to create ultra-high vacuum conditions. Liquid nitrogen is used to attain temperature close to 77 Kelvin. Cryogenic temperature acts as a sink for impurities in the vacuum. Thus, the vacuum levels should be several orders of magnitude higher for film deposition in these conditions. Apart from this, the substrate can also be placed onto a rotating platter which can be heated to desired temperature levels during operations. Organic semiconductors can also be deposited via MBE. In these cases, instead of atoms, molecules are evaporated and subsequently deposited on the substrate. Other than this, gas source MBE, analogous to chemical vapor deposition, is also available. To deposit oxides or other compounds of the precursor elements, reacting gases may also be introduced into the reaction chamber of MBE. Such films are of particular interest in advanced electronic, optoelectronic as well as magnetic applications. Typical uses of MBE: being able to deposit high purity uniform thickness film of a diverse range of compounds. MBE is extensively used to produce semiconductor lasers for CD players, advanced computer chips, low temperature superconductors, solar cells, where a thin film of photovoltaic material is deposited on a substrate. Other than industrial uses, MBE is also widely used in advanced nanotechnology research activities. In brief, precise MBE has applications in thin film computing devices, optics, photonics, etc. Now students, let us see the advantages and disadvantages of MBE. The advantages of MBE include: it can be used to prepare high quality, defect free and highly uniform semiconductor crystals of a wide array of compounds, and also precise control over film thickness is possible in MBE. The disadvantage of MBE include very slow deposition rates, which result in very long residence times. Additionally, it is a laborious technique. Thus, this technique is more suitable for scientific research purposes, and commercial production using this technique is expensive. The equipment is very complex and expensive, which originates from the requirements of extremely clean and ultra-high vacuum conditions. Who invented MBE? Alfred Y. Cho and John R. Arthur Jr. are credited with the invention of molecular beam epitaxy technique. They developed the technique in 1968 while working at the Bell Laboratories. After its discovery, several scientists have made significant contributions to the development of modern day MBE systems. These include, but not limited to, Leo Esaki won the Nobel Prize in 1973 for pioneer works in semiconductor electronics, and Ray Tsu working at IBM. First, first in 2009, Nanotechnology International Prize Russanano Prize was awarded to Alfred Cho for developing MBE technique. Fabrication of quantum dots by MBE method. The growth of epitaxial, either homogeneous or heterogeneous thin film on a single crystal surface strongly depends upon the strength of interaction between atoms and the surface of the substrate. Most of the MBE processes involve growth of films epitaxially by vapor phase approach. However, it is also possible to grow epitaxial layer, often termed as epilayers, from a liquid solution. The growth by MBE can be divided into three types, depending upon the lattice mismatch between the film and the substrate. These are 3D growth, 2D growth, and Stransky-Korsanov growth. 3D growth occurs when the interaction between add-atom are stronger than the interaction between add-atom and the substrate, resulting in the formation of 3D and atom clusters or islands. For the reason 3D growth mode is often referred to as island growth. The formation of cluster makes the deposited film coarse. Thus, the film grown by 3D mode are usually rough and multi-layers are certain points. In contrast to 3D growth, the interaction of atoms in 2D growth are stronger with the substrate surface than their interaction with the other atoms. Therefore, atoms prefer to attach to the surface sides, leading to the formation of atomically smooth, completely formed layers. This layer by layer growth is two-dimensional, indicating that complete film form prior to the growth of subsequent layers. In this regard, Stransky-Korsanov mode is intermediate to both 2D and 3D growth modes, and thus both types of growth occur in this mode. Transition from the layer by layer to island type growth occurs at critical layer thicknesses, which strongly depends on the chemical and physical properties such as surface energies and lattice parameters of the substrate and the film. The homogeneity in both size and shape of the quantum dots assembled is an important parameter that influences the optical performance of the device fabricated from them. This factor can be improved if the quantum dots are literally ordered or periodically aligned along some specific crystallographic direction on the surface of the substrate. Additionally, a long-range ordering of quantum dots is highly significant for future micro and optoelectronics devices that the exploitation of these properties of a single or a well-defined number of nanostructures. The AFM image of indium arsenide dot arrays on indium gallium arsenide over gallium arsenide substrates. So inset of this figure shows the structure of a single indium arsenide quantum dot. Quantum dots are structures where carriers are confined in all the three spatial directions and where zero-dimensional systems of carrier are realized. This can be achieved by embedding the self-assembled islands within the layer of semiconductors, having large energy gaps and suitable band discontinuities. When the size of 3D islands approaches the de Broglie wavelength of the carrier and their mean free path lengths and the carriers are quantum confined within the levels in the quantum dots. This usually occurs in the semiconductors because the de Broglie wavelength approaches a few tens of nanometers. Molecular beam epitaxy is a widely employed technique for producing quantum dot structures. The spontaneous formation of MBE quantum dot assembles due to a mismatched heterostructure is attracting huge interest in both fundamental research as well as practical applications. So students, let us now summarize what we have learnt in this module. We have understood the working principle of molecular beam epitaxy. We have seen its uses in practical application, its advantages and disadvantages, and we have also studied about the history of MBE and also understood how it is used to fabricate quantum dots. Thank you.